Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. This is second part of the third chapter, Limits and Continuity. In this session, I will discuss the sequential criterion for limits. So before looking at the criterion, I want to state a few things. Supposing I have a function from a set A to the set of real numbers. Okay, so let small f be a function, some function from a set A to the set X, let's say set R, and in this set A, I will take one sequence Xn whose elements or the terms of the sequence are from the set A. Okay, so this sequence is a sequence inside A. So all the points x1, x2, x3, x4 of the sequence, they are sitting inside A. Then from this sequence, I can obtain one more sequence f of xn, alright, and the terms of the sequence will be the images of the sequence xn under the function f. So this sequence, new sequence will be f of x1, f of x2, f of x3, and so on. Okay, so this new sequence which is obtained is denoted by this f of xn. Okay, so it's a sequence whose terms are nothing but the images of the sequence xn that I started with here under the function f. Alright, so with this understanding, I will move on to the sequential criterion for limits. So the sequential criterion for limits says if J is an interval in R and A is any point in J, supposing f is a function from J difference A to R, then the following statements are equivalent. Okay, so when I say that two statements are equivalent, if whenever one happens, the second one also happens. If one does not happen, the other one will also not happen. Right? So they are of the form P if and only if Q. So what it says is, it talks about limit of a function at a point in terms of sequences. Okay, sequences we have already seen in the last chapter. So limit x tending to a f of x will be equal to L if and only if whenever I take a sequence in J difference A, for every sequence xn in J difference A, such that that sequence converges to A, whenever this happens, the image of that sequence, that is f of xn, this sequence I just defined, this f of xn will converge to this limit. If this happens, then I can say that limit of the function is L as x tends to E. Alright, so what the second criterion, second statement says is, whenever I pick up a sequence xn, okay, in J difference A, such that xn converges to A, whenever this happens, then image of this sequence, that is f of xn, this new sequence will converge to the limit A. Okay, so whenever sequence xn converges to A, its image sequence f of xn will converge to L. This is what it says. Okay, the second point. So we want to show that these two statements are equivalent. Okay, so what we will do is, we will assume 1 and prove 2, and we will assume 2 and we will prove 1. So let's assume 1 and prove that 2 will hold. Okay, so here goes the proof. 1 implies 2, or you can say this one. Okay, I want to show that 1 implies. So I'll assume that limit of this function as x tends to a is L. This is my assumption. What I want to prove, if xn is a sequence in J difference A which converges to A, then f of xn will converge to A. Okay, so if part I will have to assume and then part I will have to prove. So I will start with a sequence xn in J difference A such that xn converges to A. And what is the claim? We are claiming that f of xn will converge to L. This is our claim. Okay, this sequence f of xn converges to L. Right, so we have already dealt with uh, such convergence of sequences. How do you show that a sequence converges to some real number? Okay, so supposing epsilon is some positive number which is given to us. Okay, so we have to show that after a certain stage, all the terms of the sequence, this difference can be made less than epsilon. F of xn minus L can be made less than epsilon. Now, since limit as x tends to a, f of x is L, okay, for this epsilon, given epsilon positive, by definition of limits that we saw in the last session, I can find a delta greater than 0 such that, given any epsilon positive, I can find a delta greater than 0 such that whenever I take points x in J with the condition that x difference A is less than delta, this will imply that f of x minus L will be less than epsilon. This is by definition of limits that we discussed in the last session, right? So you give me any epsilon positive. For this epsilon positive, I have found a delta positive here such that whenever x difference A is less than delta, f of x minus L will be less than epsilon, where J, the point x is from the set J. That's the interval in R, right? Also, we are assuming that the sequence xn is converging to the point A. Okay, so since xn converges to A, also xn converges to A. Okay, so for this epsilon positive, same epsilon positive, I can find a natural number capital N such that for all n bigger than or equal to this capital N, after this stage, xn minus A can be made less than epsilon. This is by definition of convergence of a sequence. Okay, so there is a stage capital N such that for all n bigger than or equal to this capital N, xn minus A will be less than epsilon, right? Now this definition works for any epsilon positive, right? In particular, it will work for the delta positive that we have obtained here. So for this delta positive which we have obtained, for this delta also it will work. So for delta greater than 0, I can find a natural number such that for all n greater than or equal to capital N, modulus of xn minus A will be less than delta, right? It works for any positive number. Epsilon I use because that's how we had defined it. But now I'm applying it for delta positive. So for this delta positive that we obtained in the previous step, this condition will work, right? And the sequence xn, the terms of the sequence xn here, they are from J difference A. So they are in J except possibly the point A. Fine. So for all the points now xn where n is greater than or equal to capital N, this condition will also work because it works for all the points in J whenever the point in J difference A is less than delta. This is going to happen. F of x minus L will be less than epsilon, right? So if I combine both the conditions, what do I have? Okay, so for all n greater than or equal to capital N, xn minus a is less than delta, right? Now since xn's are points in J, okay, and J difference A you can say, and xn minus A from here is less than delta, okay, for all n bigger than or equal to capital N. So by this condition, this implies it satisfies, now these xn's after the stage capital N, they satisfy this condition, that is this condition they satisfy. That means this implies this, so this will imply f of xn minus L will be less than epsilon for all n greater than or equal to this capital N. Okay, so this is coming by star, and I will name this statement as star, right? So what we have done, therefore, given epsilon positive, we found a natural number capital N such that for all n greater than or equal to this capital N, f of xn minus L is less than epsilon, and hence we have proved that the sequence f of xn converges to L. Okay, and that's what we had to prove statement number 2 here. So if I take a sequence xn in J difference A which converges to A, then f of xn will converge to L, right? So we have proved 1 implies 2. Now to prove the converse, that is 2 implies 1, conversely, that is 2 implies 1 I need to prove now. So we will assume 2. Assume that given any sequence xn in J difference A with xn converging to A, we have f of xn converges to L. That's the assumption, and we want to prove statement number 1, that is limit x tending to A, f of xn is L. This is what I have to prove, right? Let's assume that the limit is not equal to L. So we will assume that this statement is false, which I want to prove, and we will arrive at a contradiction. Okay, so we will assume that limit x tending to A, f of xn is not equal to L. Okay, so this is the assumption that this limit is not equal to L. We have to arrive at a contradiction. So what will be the contradiction is, we have to find a sequence xn which converges to some point A, and then we'll have to show that f of xn does not converge to L. So that will be a contradiction to this assumption, which I'm calling, let's say, double star now. Okay, so I have to arrive at a contradiction for double star. Now, when do you say that limit of a function is not equal to L? If I go back here, what do you mean by limit of f of x is L as x tends to A? Given epsilon positive, I can find a delta greater than 0 such that this happens, right? So I have to negate this statement now, and what is the negation of that? I will state here. So limit of f of xn as x tends to A is not equal to L, right? So therefore I have to negate the definition now. So there exists an epsilon greater than 0 such that for all delta greater than 0, that condition will not work. Okay, so there exists epsilon positive such that for every delta positive, no matter what delta positive you take, okay, there exist points in J. There exist points x naught in J such that whenever x naught minus a is less than this delta, this will imply f of x naught minus L is not less than epsilon. And if it is not less than epsilon, that means it must be greater than or equal to epsilon. So no matter what delta you pick up, okay, no matter what delta you pick up, you will be able to find at least one point x naught in J. This x naught will depend on delta. Okay, you will be able to find at least one point x naught in J such that whenever x naught minus a lies between 0 and delta, its modulus, it will imply that f of x naught minus L is bigger than or equal to epsilon. Okay, so you will be able to find one such epsilon. Now in particular, if I choose for delta n equal to 1 by n for each natural number n, okay, if I pick up delta n to be this, so delta 1 is 1, delta 2 is half, delta 3 is 1 by 3. For all these deltas, this condition will not work, right? So no matter what delta you pick up, this will definitely happen. So for delta n's equal to this, for delta 1, delta 2, delta 3, for all these delta n's also this condition will happen, right? So for delta 1, I will be able to find one point x1 in J such that this happens. For delta 2 equal to half, I will be able to find one point x2 for which this condition happens. So in general, for delta n equal to 1 by n, there exists a point xn in J. Okay, there exists a point xn in J such that whenever 0 is less than mod xn minus a is less than delta n, this will imply that f of xn minus L is less than epsilon, sorry, is not less than epsilon. That means it is greater than or equal to epsilon, right? So for each delta n's, this is going to happen. Now if you see, if you try to analyze this, xn minus a, mod xn minus a lies between 0 and delta n, implies that mod f of xn minus L is bigger than or equal to epsilon, right? So 0 is a constant sequence which converges to 0. So by sandwich lemma, 0 converges to 0, right? Because that's a constant sequence converging to 0. What you can say about the sequence delta n is nothing but 1 by n. So that converges to 0. So these two converges to 0 and xn minus a is strictly lying between them. So xn minus a will also converge to 0, which implies xn converges to a. So this points sequence of points xn which I obtained from here is converging to a. But f of xn minus L, you cannot make it less than epsilon. Okay, but f of xn does not converge to L. So we have found a sequence xn which converges to A, but the corresponding image sequence, that is f of xn, is not converging to L. And what did we assume in the beginning? If you pick up any sequence xn in J difference A which converges to A, then f of xn should converge to L. Double star I have marked it as. Okay, so that's a contradiction to double star. So this is a contradiction to double star. So why we are getting this contradiction? Because we assume that the limit of this function as x tends to a is not equal to a, and hence limit x tending to a f of x is equal to L, and hence we have proved that 2 implies 1. Okay, so we conclude that these two statements are equivalent to each other. Okay, so this is called sequential criterion for limits, another way of talking about limit of a function at a point. All right, so that's it for this session, and these are my references. Thank you.